Hi everyone, my name is Lydia and this is what I wish they taught me about econometrics and introduction. In this video, we're going to talk about the central limit theorem. We mentioned it when we first talked about the seventh assumption of the OLS statistical properties. And in that particular assumption, we had that the error term was normally distributed. Now, I have written in this parallel block why variable normally distributed, and that is because students have this misconception that when you do regressions and when you run OLS, you have to very carefully look at the distribution of the y variable. So the misconception is that the y variable needs to be normally distributed. However, keep in mind, when we went through all of our assumptions for the OLS, we never talked about the distribution of the y variable or x variable at any point. We only concentrated on the distribution of our error term. And that's where all the misconception starts from, because in fact, due to the central limit theorem, you could have a y variable that is very unsymmetric, that is very ugly distributed in the sense like let's say that these are your observations for the population, and if I did it a little bit nicer to show like how exactly that gets distributed, it goes as something like this. So it can be very unsymmetric, very ugly. It doesn't have to be normally distributed as you see, but that will not change once or anything that you do once you do the central limit theorem and you apply the central limit theorem. So one of the questions that will come to you would be, well, what happens to the randomness when you're applying the central limit theorem? And the idea is that randomness, in a sense, cancels out when you average. And this is the process that we will see now with the central limit theorem and how it actually operates. So let's look through that process and how exactly we get to this idea of canceling randomness through averaging. So imagine that you pick one random person and record their income at that point. So one person, and you record the income. Imagine that you have your usual Excel spreadsheet basically, and the first person here, ID number 1, you get the income, you record it. Now, when you picked this person, it's very random. So this one observation that you picked in here out of your population, it's literally pure randomness, okay? By pure randomness. And keep in mind, the number that you have for this income, it can be a very high number, it can be a very low number, it can be even very far from what you typically expect to see as an income for someone. But that still is purely random. Okay, so in this particular population graph in here, we would have literally just like, let's say, picked this one particular observation in here. Now, instead of picking one person, let's say that we pick 10 people out of the population. So let's say we pick randomly 10 points. 1, 2, 3, 4, 5, 6, 7, 8, 9, and let's say 10. Okay, so all of the dots in red. Hopefully I have 10. Let's say you pick all of those 10, you'd be listing them in your Excel spreadsheet, you would be recording their incomes in here, and ultimately you will find an average income. Now, look at when I picked these observations in here. I have this one that looks quite extreme, and then this one that looks quite extreme as well. So overall, it does seem like we've got some very differing numbers in here. But what happens the moment that I'm actually averaging this income? Well, it's either high values that pull up the average. Okay, so pull the average up. Okay. And then very low values they pull it down. Okay? But by doing that, in a sense, they are starting to cancel each other out. In other words, extremes fight each other when you average. Now, instead of you taking just one group of 10 observations, imagine you repeat this process. So now the procedure is you pick a group of 10, you find the average, and you put that average in a graph. Okay? Then you pick another 10. You compute the average. So another 10, you compute the average, you put that in a graph. And you keep repeating that. And every time you record. Now, keep in mind, every time you pick your sample of 10, you're doing it purely out of randomness. Still random. Okay? So how exactly is it starting to cancel out or for it to become weaker? Well, the thing is, the moment that you are now computing this average and you're putting that average into its own graph, now you will start to see patterns in the kind of averages that you are seeing. And that's where you're going to see that randomness becoming weaker. So what's going to happen is that most averages, okay, end up being clustered to the true mean. While extreme averages, they become rare. Okay, so basically, translating it graphically, what we're doing is, let's say this is the mean, and the axis here is where you're seeing all of the means out of all of these samples. So let's say you say, this is not a zero, by the way, right in the middle, let's say that we expect the average to be like 30,000. So let's say you'll see average here, and then here, and here, here. You'll see some extreme averages in here, maybe, or even here on the other extreme, but most of them will start piling up averages and observations one on top of each other here. Okay? If you keep filling this up and you repeat this, let's say 100,000 times or 1,000,000 times, then that's when the number of observations is going to increase, and you will notice that that bell-shaped curve finally taking shape. And this is the heart of the central limit theorem. Okay, so keep in mind, every time you're picking your sample, that is a purely random event. However, you are now putting into the graph the averages that are coming out of these samples. And what you will notice is that most averages will end up close to the true mean, while extreme averages are going to become rare. Now, why the shape becomes normal? When randomness cancels out in many like small pieces, the results tend to pile up here in the middle, as I said, and thin out in the edges because they become more rare. That is to say, well, I'll still, even if it's random, I could still end up getting the sample of 10 people that all have higher income. But that doesn't mean that it doesn't exist as an opportunity, as a chance for it to happen, okay? So I still have it here. It's just, it's going to be quite rare for me to end up there, okay? But the probability has not disappeared entirely. Now, that smooth pile that you will start seeing here in the middle, and then the thinning out in the tails, that is your bell-shaped curve or the normal distribution curve. Okay, so keep in mind, normality in this case it's not assumed. It's actually what emerges out of you doing that process over and over again. And keep in mind, econometricians care because when we do our inferences and when we talk about OLS coefficients, we are looking at averages of random things. So we always talk about averages of errors, average products of something, and so on. Okay? That's why coefficients need to look normal in large samples for the t-test to work. And we don't necessarily need to have the assumption of the normal errors fully given to us. The central limit theorem is this white engine behind the entire econometric inference that makes sure that if you have a large enough sample, even if your population started to look not so normal, you will still have, when it comes to your coefficients of the OLS, a distribution that looks normal, where you can then use your t-test and the standard normal and the standard errors. So keep in mind, randomness does not disappear, it's simply averaging out. And when it does, that's when normality shows up. Okay? There is a website online that can help you see that visually, so make sure you also check online statbook.com for that. But otherwise, I hope these helped you get a little bit of the intuition behind what's happening with the central limit theorem, and I'll see you in the next video.